I will definitely wait a little longer. There's only 10 of you in here so far. As you noticed, I had to set up a waiting room and me admit everyone individually. That's a new district requirement for all Zoom meetings of any kind.
They have to log in.
Did it require a password?
No, it didn't require a password.
Oh, that's weird. I thought it would.
I didn't need a password either.
Yeah, you just click on the link and then it takes us right to the Zoom.
But you had to wait for me to admit you in, right?
Yeah.
I had to use one.
I do have it set to automatically record from now on, so didn't even have to remember. Okay, well, it's been 5 minutes. If people join sometime later, I'll watch it and let them in. So, a few things before we begin our lesson. Over the next few days, you'll be getting information from me, school and district about how grades are going to be from here on. I know at the beginning of all this, I said that we weren't doing grades when we first started this, but things are constantly changing, especially over the next 3 weeks, when that first rule doesn't really apply to that, because the next 3 weeks we're having off because the governor said that we had to be off. So you'll get some information later this week about what grades will look like over the next month and what we're doing with third and fourth marking period. And really almost anything that you are told over time may be changed a few days later. But just keep that in mind. And I'm going to wait till they send out district information to you before I tell you what that's going to specifically look like for us. There is we finished a series on Friday, and there's a card match type thing for that we would have done on the review day if we were in school. I'm thinking we will probably go over that in a few weeks, like right before the AP exam. Because starting Wednesday, we'll start reviewing for everything, and then just as we get to review Unit 10, we'll do that. The goal for this week should be is learning Taylor polynomials, which is what we're going over today and Wednesday, and then reviewing Unit 1 over limits. On the Google Classroom, I have 2 assignments other than watching the video, which hopefully you did watch. The humongous review sheet, and the due date on that one's just a guideline. I mean, if you want to do each different unit's definitions, theorems, and whatever over time over the next month, that's perfectly fine. And then the other thing on the other assignment on the Google Classroom is a limits review. Because we haven't really done limits in quite some time. So that limits review is currently up, and it currently says the due date is next Wednesday. Okay. And then when we start doing review next week, the only real lesson that we're going to do is I will give out assignments to you over time, and the only thing I'm really going to be going over with you highlight some major things that we need to remember from previous units, obviously, and then go over any assignments that I ever give you. That's what my lessons will be. Other lessons that you should watch definitely during review time is the AP Calculus BC review session videos. The link to that is in both the Remind and the Google Classroom. Okay. Any questions about any recent material before we go on to the next lesson?
Like homework question or?
Yeah, I mean, if you have a homework question, we could answer that before going on to Taylor Polynomials.
I was having a hard time figuring out number 11 on the last series page we did, 115.
The review page?
Yeah.
Page 115, number 11. So on that one, we're doing the limit, not limit, we're doing the sum from n equals 1 to infinity of natural log of 1 plus 1 over n. And in the key, they are comparing it to just 1 over n. They're comparing it to 1 over n. And one reason why they chose to do that is when we take the limit of both of them, you'd be able to put them together. And so, let me go back to the Zoom. I'll share my screen to show that. Okay, so they're going to do the limit comparison test. On this one, I mean, if you were to do like process of elimination, try to figure out which test to use, this is not in any of the forms. This does not look like a p-series or a geometric series, not alternating or telescopic. So it's not any of those forms. So then we go through the other list and just try the easiest one first and so on. Well, ratio test would not work well here. There's no n's to a power, or there's nothing to the n power, and there's no factorials. So that one wouldn't work nicely here. And then the next easiest one after the ratio test is limit comparison test. So trying the limit comparison test, we're going to compare it to the sum of 1 over n. The reason for 1 over n is that is similar to this, that is part of this. the sum of 1 over n is similar to this, and it is part of this. And when we take the limit, when we do the comparison, we know ahead of time we're going to have to do L'Hopital's rule, because these are going to end up on top of each other. And as 1 over n goes to infinity, that goes to 0. As natural log of 1 plus 1 over n goes to infinity, that also goes to 0, because that fraction would go to 0, leaving you with natural log of 1, which is 0. So you'd end up with 0 over 0. When you take the derivative, when you do L'Hopital's rule, this thing would go away. Then you'd only have just polynomial type things on top of each other that could simplify. So then doing limit comparison test, limit as n approaches infinity of 1 over n over natural log of 1 plus 1 over n. That does go to 0. That does go to 0. So then we do L'Hopital's rule. Well, limit as n approaches infinity. Derivative of 1 over n is negative 1 over n squared. I should have that's a value sign on that. And then derivative of this. Well, it'll be derivative of the inside over the inside, because that's derivative of natural log terms. Derivative of the inside over the inside, u prime over u. So, well, the derivative of the inside derivative of 1 is just 0, so it's just derivative of this, which is the negative 1 over n squared over 1 plus 1 over n. Okay, now to continue simplifying this, it's going to be the limit as n approaches infinity of, well, we have this fraction on top divided by this fraction here. If we flip and multiply that, we just get negative 1. Well, really, this fraction up here, just to be a little more clear, it's like it's over 1. Like we have that, and then that big fraction, which is kind of nasty. Negative 1 over n squared, kind of over 1, times 1 plus 1 over n over negative 1 over n squared. That would cancel with that. We just have the limit as n approaches infinity of 1 plus 1 over n. Well, that would approach 1. That would approach 1. And based on the limit comparison test, as long as the limit is positive and finite, they will do the same thing. The limit is positive and finite, which 1 is, they will do the same thing. Well, this sum of 1 over n, that's the divergent harmonic series. So that diverges. And since the limit as n approaches infinity of a sub n over b sub n, well, really b sub n over a sub n is how I did it. B of n, a of n. So I have the limit as n approaches infinity of b of n over a of n. That ended up equaling the positive finite value of 1. So they're going to do the same thing. So this diverges as well by limit comparison test. Okay. Well, we're going to go on to Taylor polynomials now. So on Friday, when we were doing Taylor polynomials, we started off with the idea that a Taylor polynomial is essentially taking a polynomial, which is a cubic is a polynomial, a quadratic, a linear, a quartic, a quintic, like those kind of things, x to some power times a coefficient plus another x to some power times a coefficient. That's a polynomial. And so it's taking a polynomial and using a polynomial to approximate other functions that are not as nice to use. For instance, e of x, natural log, cosine, sine, some of the most common ones to use Taylor polynomials for, because they are more difficult to deal with, but a polynomial is not. So we were, on Friday, taking our function f of x equaling e to the x and coming up with polynomials that approximate the value of that function very close to some specific value. And our specific value was 0. We found the first degree polynomial, which would be using the first derivative. The first degree polynomial is just linear. And we found that first degree polynomial to be x plus 1. So it ended up looking like this. And so really it's just a tangent line to e to the x at x equals 0. And then we found the second degree polynomial, which is a quadratic, which is then going to hug the curve a little longer. It's going to be a parabola around x equals 0 on the function. And now we're going to find the third degree Taylor polynomial. A third degree Taylor polynomial is going to be a cubic and use the third derivative. So it would be in the form a sub 3x cubed plus a sub 2x squared plus a sub 1x plus a sub 0. We need to figure out what a sub 0, 1, 2, and 3 are. And again, our function is e to the x. Well, hopefully we noticed that when we found the second degree Taylor polynomial, a sub 0 and a sub 1 were the same as they were when we found the first degree Taylor polynomial. And that's going to be the case continually, no matter when you find degree polynomials. We don't need, if we want to find a fifth degree Taylor polynomial, well, we can just take the fourth degree and then add one term. And it's a similar idea here when we're about to find a third degree polynomial. We can use all of our information we've already used for the second degree polynomial, then just also add one more term. We already know a sub 0 is going to be 1. A sub 1 is also going to be 1. And what did we get for a sub 2 when we did the second degree polynomial? For a sub 2, we got that is 1/2. A sub 2, we got it was 1/2. So that's just information we already found on the previous page. So now, to get the next term, to make it a third degree polynomial, we're going to have to use the third derivative, and that also makes it cubic because it's a third degree polynomial. Really, the word degree here can refer to the kind of polynomial it is. Quadratic, cubic, quintic, quartic, all of that. The word degree also refers to how many derivatives are needed. Okay, so we need the third derivative of the polynomial at 0 to also equal the third derivative of our function at 0. Well, our function is still e to the x. What is the third derivative of e to the x? Well, it's still going to be e to the x. That's never going to change. That's nice. Meaning f triple prime of 0, well, that'd be e to the 0, which is 1. Anything to the 0 is 1. So f triple prime of 0 is 1. And we need to make sure that p triple prime of 0 is also 1. Well, then let's find the third derivative. Well, the first derivative of this p prime of x, first derivative would be 3. a sub 3x squared plus 2a sub 2x plus a sub 1. Then the second derivative would end up being 6a sub 3x plus 2a sub 2. And the third derivative of the polynomial would just end up being 6a sub 3. And so we need that 6a sub 3 to end up equaling 1. So that means that a sub 3 equals 1/6. So now that we got that, we can write out our polynomial in this form up here. So that means we have 1/6 x cubed plus 1/2 x squared plus x plus 1. And so that is then a cubic that will hug the e to the x function around x equals 0 even longer than the quadratic did. And each higher degree polynomial we come up with is a more accurate approximation of the function than the previous one, and then has closer approximations to the actual value for a longer period of time. And so if we were to graph that cubic here, this solid line is the e to the x, and this dashed line is the cubic. And if you compare it to the graph on the previous page, it is more accurate for a longer period of time than the quadratic was. And that just keeps happening the further you get. You come up with a 4th degree, a 5th degree, and so on. Well, as we keep taking derivatives, I want to address something real quick. P of x. Okay. What would be the 4th degree Taylor polynomial? What would it look like? Well, the 4th degree, all of those terms right there would be the same. We'd just have one more term in the front of a sub 4 x to the 4th plus a sub 3 x cubed plus a sub 2 x squared plus a 1 x plus a sub 0. Okay. Well then, based on what happened with the cubic one, what would then be the 4th derivative of this polynomial? Well, after the first derivative, a sub 0 is gone. After the second derivative, that term's gone. After the third derivative, that term's gone. After the 4th derivative, that term will be gone because that's what happened up here. After the first derivative, a sub 0 went away. After the second derivative, a sub 1 went away. It's gone. When we took the derivative a third time, a sub 2's term went away, and we were just left with this of taking the derivative of the first term that many times. So if we take the derivative of the first term 4 times, what will we end up getting?
24.
It will end up being 24a sub 4. Well, we want the 4th derivative of our function to still equal 1. Well, the 4th derivative of e to the x is still e to the x. So the 4th derivative at 0 is still 1. That's why it's going to still be 1. So a sub 4 is then going to be 1/24. Okay. So a sub 0 was 1. I could also write it as 1/1. A sub 1 was 1. I could also write it as 1/1. A sub 2, 1/2. A sub 3 was 1/6. A sub 4 was 1/24. If we look at the denominators, because those are the things that are changing, It goes 1, then 2, then 6, then 24. What is happening with the denominators with each new degree polynomial?
There's a factorial happening.
Yes, there is a factorial happening. Because also each new one is, it's the degree of the polynomial. A sub 4 is the fourth degree, is from the fourth degree polynomial. This is the coefficient in front of the fourth degree polynomial. Is in front of the term with the fourth degree, and it is 4 factorial on the bottom. The coefficient in front of the 8x cubed is 1/6 and has 3 cubed on bottom. The coefficient in front of x squared is 1/2, meaning having 2 factorial on bottom. So the denominator of all these coefficients ends up being the degree of the polynomial factorial. So that is why if we then make a fourth degree polynomial, it would end up looking like this. The 1 plus x squared plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed plus 1 over 4 factorial x to the fourth. Any guesses as to what the next term would be for a fifth degree polynomial?
1 over 5 factorial times 5 to x to the 5th.
Yep, that's what it would be for the fifth degree polynomial. So these are all polynomial approximations around the function of the function f of x, e to the x, around x equals 0. This particular one for e to the x, that does need to be memorized. There are 3 that should be memorized: e to the x, cosine, and sine. Okay. So that's just a further explanation, and we're going to skip that little next section now to talk about this box. So this box is now just an example formula. Notice this first one here, Taylor polynomial of f of x at x equals c. This is pretty much what we were doing. But what was our c value? What did we have the function centered at?
0.
We had it centered at 0. So the specific Taylor polynomial that we were actually doing for e to the x is really called a Maclaurin polynomial. It's called a Maclaurin polynomial when your c is 0. And so this function here, this polynomial, would be the Maclaurin polynomial, which is just a Taylor polynomial centered at 0. And this right here is the formula for any function. The reason the one we did looks extremely similar to this one is just because the derivative, no matter how many times you take the derivative at 0, is always going to be 1 for the e to the x function. So with e to the x, we had 1 plus 1 times x plus 1 over 2 factorial times x squared plus 1 over 3 factorial times x cubed, and so on. That's just the function at the point. That's the first derivative at the point, second derivative at the point, third derivative at the point. Once you get to fourth derivative and so on, we just put that number in parentheses right there where we'd normally put the primes. But then a normal Taylor polynomial, it could be, a Taylor polynomial could be centered anywhere. It doesn't really matter where it's centered. You would be told where it was going to be centered though, if you were to make one. And so this is the first 4 terms of a Taylor polynomial, that formula, and then the formula in general, meaning the nth derivative at c over n factorial times x minus c to the n power. So we could have had it centered at e, or centered at 1, and then just 1 would be in the c spot over and over again. But if c is 0, then that just automatically makes it look like this. Okay, let's come up with some other ones. Practice doing this. So in this next one, we're going to find the Taylor polynomials, first degree, second, third, and fourth degree Taylor polynomials for the function natural log of x minus 1. Centered at c equals 2. natural log of x minus 1 centered at c equals 2. Is it possible for them to have asked us to have it centered at 1?
No,
Why not?
the function doesn't exist at where natural log x equals 0.
Yes. Yeah. So you're never going to. So that therefore means that there's no such thing as a Maclaurin polynomial for natural log of x. Because a Maclaurin, or like just if your function is just natural log of x, can't be a Maclaurin polynomial for that because natural log doesn't exist at 0, and a Maclaurin it's centered at 0. Okay, so we're gonna just nicely go through this table. So what is the derivative of natural log of x minus 1?
One
You get 1 over x minus 1. Again, the derivative of natural log of something is just derivative of the inside over the inside. Well, the derivative of x minus 1 is just 1 over the x minus 1. Then f prime of 2. Well, just plug 2 into that, and we would get 1. And so this is going to be a first degree Taylor polynomial. A first degree would have 2 terms. It's a linear equation. And it would be, well, oh, what is f of 2?
0.
F of 2 is 0. So then the first degree polynomial will just be what? The first degree just uses the first 2 terms. F of c plus f prime of c times x minus c. Well, f of c here is 0 plus f prime of c, our f prime of c was 1 times x minus c. So times x minus 2. And so that's it. So I'm going to write it like the formula. So 1 times that plus 0. Because I should have had it switched. I'll do that for the rest of them. Okay, then second degree Taylor polynomial. Well, not just second degree derivative right now. So that will be the derivative of this right here. Well, we can think of that term as x minus 1 to the negative 1 power. So just chain rule that. That's going to give us the negative would come down. So we'd have negative 1. The new power would then be negative 2. So this negative, it's going to be in the bottom still, but squared. So negative 1 over x minus 1 squared. Well, now if x is 2. If x is 2 now, we'd have 2 minus 1, which is 1 squared is still going to be 1. So we just have negative 1 there. So then I'm going to put f of c first. So we have 0 plus 1 times x minus 2 plus a negative 1 times x. Wait, negative 1 over 2 factorial times x minus 2 squared. Because the negative 1 is the second derivative at 2 over 2 factorial times x minus 2 squared. I'm just using the formula for the Taylor polynomial from the previous page. Now the third degree polynomial. Well, what's going to be the next derivative? What's the third derivative? That could be thought of as negative x minus 1 to the negative 2 power. When you do chain rule, that -2 can get multiplied down, so it'll become a +2 over. The power will go down 1 to -3, so it's negative, it's still going to be in the denominator, but now cubed. -1 cubed. When plug in 2, 2 minus 1, 1, 1 cubed, still 1. So we just got +2 there. Well, in the third degree polynomial, these three terms are still going to be there. 0 plus x minus 2 minus x minus 2 squared over 2. Then plus, well, so the third term would need to be the third derivative at the point. So 2 over 3 factorial times x minus 2 cubed. Then the fourth derivative. Well, that is just 2 times x minus 1 to the -3 power. We take the derivative of that. -3 times 2, -6 over x minus 1 to the 4th power. When plug in 2, 2 minus 1 is 1, 1 to the 4th is still 1. So we just have a -6 there. All those terms are still going to be the same as they were. We're just adding one more term for the 4th degree. 0 plus x minus 2 minus x minus 2 squared over 2. Okay, let's simplify this a little bit. 3 factorial is what?
6.
Yeah, that'd be 6. And so we'd have 2 over 6, which is 1/3. So then we have x minus 2 cubed over 3. Now put our 4th term, which is -6 over, it's the 4th degree in our 4th term in our 4th degree polynomial. So this is 4 factorial times x minus 2 to the 4th power. Okay, now if we simplify things a little bit, our 1st degree polynomial was really just x minus 2. Our 2nd degree polynomial was really just x minus 2, but then plus this term here. So x minus 2, then minus x minus 2 squared over 2. Our 3rd degree polynomial is just that 2nd degree of x minus 2 minus x minus 2 squared over 2 plus x minus 2 cubed over 3. And then the 4th degree, it's going to be that same term, x minus 2 minus x minus 2 squared over 2 plus x minus 2 cubed over 3. Then next is minus, well, now we're just simplifying that last term. Well, 4 factorial, we said earlier, was 24. So we'd have 6 over 24, which is just 1/4. So it's x minus 2 to the 4th power over 4. Okay, that was, yes, a lot of work, but hopefully we see a pattern now of our 5th degree polynomial. It's going to be this same 4th degree polynomial, and then plus the 5th degree term. And so what is our 5th degree term going to be in the 5th degree polynomial based on the pattern that's happening here?
X minus 2 to the 5th power over 5.
X minus 2 to the 5th power over 5. Yep. And then the 6th degree polynomial would still have that 5th term of x minus 2 to the 5th power over 5. And then what would be the 6th degree term?
X minus 2 to the 6th power over 6.
2 to the 6th power over 6. And what should be the sign right here?
Negative.
Negative.
Yep, negative. Awesome. Okay. And in that entire process, we're just really using that formula, that each degree polynomial, it's that degree's derivative at that point over that degree factorial times x minus c to whatever that degree is each time. So that's one way that helps remembering the formula, because as we look at the formula, notice I could put that as, I could put this right here as over 1 factorial. I could put this as over 0 factorial. Then I could also, x minus c, that's to the 1st power. Anything that's just as is to the 1st power. I could call this x minus c to the 0 power, because something to the 0 power is 1. So each term, however much degree it is, there's 3 things that are the same. The factorial that's on bottom, the power of the x minus c, and the derivative. Those are all the same for each term. This right here has the 3rd degree polynomial, 3rd degree factorial, and cubic, and so on. Nth degree derivative, n factorial, nth degree power. Those 3 are all the same for each term. And that's the same thing with a Maclaurin series, with a Maclaurin polynomial. Just the only difference is here it's centered at 0. Here it's centered at 0. Okay, so I'm going to turn 2 pages. Well, this is the page we just did. And let's now go and talk about sine and cosine. So we're going to do the Maclaurin polynomials for sine and cosine. Maclaurin polynomials for sine and cosine. So for sine and cosine, we're going to come up with the derivatives, and then derivative at 0. We're doing it at 0 because this is a Maclaurin polynomial. Maclaurin polynomial has c equals 0. Essentially, it's just a Taylor polynomial, but where c is 0. The Taylor polynomial is centered at 0. Okay, so we have sine of x. Okay, derivative of sine is
Cosine.
cosine. And derivative of cosine is negative sine.
Negative sine.
Derivative of negative sine is
Negative cosine.
negative cosine. Derivative of negative cosine is,
Sine.
and it starts all over. And then negative cosine. Yeah, so that's the derivatives. Then here we want the derivatives at that specific value 0. So sine of 0 is what?
0.
0. And so that's why they don't have a piece of 0 here, because if we had a piece of 0, that would mean the 0th degree Taylor polynomial, which is just the function at that point. Well, that would just be 0. So that's dumb. That doesn't help us at all. Okay, cosine of 0 is
1.
1. Negative sine of 0 is 0. And since that's 0, that's why they don't have a piece of 2. Because each new degree polynomial adds a new degree derivative. Well, if I was to go from the 1st degree polynomial to the 2nd degree polynomial, I would be adding the second derivative at 0 times x squared. Well, the second derivative at 0 is just 0, so I'd just be adding 0. So that means there's no difference in the first degree polynomial and the second degree polynomial for sine. Then negative cosine at 0. Well, then that'll just be cosine of 0, then throw the negative on there, so -1. Then those four just all happen again. 0, 1, 0, -1. And we start making the Maclaurin polynomials. Piece of 1 means the first degree Maclaurin polynomial, which would be f of 0, which is 0, then plus f prime of 0 times x. Well, f prime of 0 is just 1 times x, so that's just x. Piece of 3, third degree Maclaurin polynomial. Well, it would just be the second degree plus the third degree's term. Well, the second degree is not here because it would be the same as the first degree since the second derivative is 0. So it's just going to be that x plus the third degree's term, which is going to be the third derivative at 0, so -1, over 3 factorial. So that gives us negative x cubed over 6. Where did I get the 6 from?
3 factorial.
Yeah. And then the fifth degree polynomial is going to be x minus x cubed over 6. And then plus the fifth derivative at the point times x to the fifth all over 5 factorial. So plus, I don't need to put the 1 times, so that's just going to be x to the fifth over 5 factorial. And then p sub 7. Well, it's going to be a fifth degree polynomial. Well, really, it's the sixth degree, but sixth degree polynomial is going to be the same as the fifth because it would be adding a term of 0. So then we have x minus x cubed over 6 plus x to the fifth over 5 factorial, and then minus x to the seventh over 7 factorial. Okay, so now we've seen that, I'm going to give you a few minutes on your own to do number 4, and then I will do it very quickly. Actually, I'm just going to stop sharing my screen. I'll do it then. I'll do it while you're doing it, and then show you what it is. So right now, work on number 4. Okay, I'm gonna share my screen again to show you answer to number 4. Okay. So, going over to the derivatives, cosine, negative cosine, sine, cosine, negative cosine. And then those derivatives at x equals 0 was 1, 0, negative 1, 0, 1, 0, negative 1. And so the Maclaurin polynomial, well, the 0th degree polynomial is just f of c, meaning f of 0, so just 1. The second degree polynomial includes a x to the second power. It includes the second derivative at the point and a 2 factorial on bottom. We just take the previous one and then add that term. And the 4th degree polynomial, we just take the previous degree polynomial. Notice since the 3rd degree polynomial was 0, since the 3rd derivative was 0, the 3rd degree polynomial would end up being the same as the 2nd degree polynomial, which is why we did not include it, because we would have been adding 0 x cubed over 3 factorial, which is kind of pointless. And then the 6th degree polynomial, 1 minus x squared over 2 plus x to the 4th over 24 minus x to the 6th over 6 factorial. Then if you look at the graphs, you can see how nicely those polynomials work out with sine or cosine near x equals 0. So the bolded graph is cosine and sine. So over here, again, we're doing it near x equals 0 right here. So that line is just the 1st degree polynomial, which is just a line. Then we have the cubic 3rd degree polynomial, p sub 3. It curves very nicely for quite a while. Like it's p sub 3 is pretty much on top of sine from -1 all the way to +1. And then p sub 5, the 5th degree polynomial, it's same as sine from like -2 all the way to +2 for quite a while. So the higher degree polynomial we can see here is more accurate for a longer period of time each further you go. And so if we took it all the way up to infinity, that polynomial is essentially sine. And then same idea with cosine. To show further what that means, let's now go to the next page. The next page says day 2 at the top, and it again gives us definition of Taylor polynomial and Maclaurin polynomial. We're asked to find the one for the 5th degree of sine. And we just did it, so we'll just rewrite that down, and we're going to do some stuff with that. So the 5th degree, it's just going to have 3 terms, p sub 5 of x, 5th degree polynomial of sine. Well, would have f of 0, but that's just 0. Then f prime of 0 is 1 times x over 1 factorial, so just x. And then it would have the second derivative at 0, but the second derivative gets you to negative sign, and it's a negative 0, 0. So to reiterate what happened previously. And you'd have the third derivative at 0, so minus 1 x cubed over 6, right? Yeah. And then it was plus x to the 5th over 5 factorial. So that is the 5th degree polynomial for sine, or 5th degree Taylor polynomial for sine around 0, or just called the Maclaurin polynomial since it's around 0. And if this has 3 terms, sometimes if you're asked on the AP exam or any free response question that I give you later on to come up with the first 3 non-zero terms of a Taylor polynomial or a Maclaurin polynomial, that is what it would be asking you to do. They may not, sometimes they may say the certain degree polynomial, and then other times they may ask for the first however many non-zero terms. So if they wanted the first 4 non-zero terms, we'd come up with one more term, which would end up being minus x to the 7th over 7 factorial, and so on. Okay. Well, now this part B asks for the 5th degree polynomial at 1.4. Well, we're going to use our calculator. for this. Parentheses, 1.4 minus over 6 plus let's see, 4 to the 5th power over okay, and I got 0.987, 0.987. I'll write the rest as well for 8.5. And then this asks, what is f of 1.4? Well, that would mean what is sine of 1.4? And so then sine of 1.4, 0.98545. And so it was rather close, only 0.02 off. Only 0.02 off. This asks what's the error in the approximation. Error is symbolized, it's going to be the absolute value of the actual function, the actual function at that x value minus the polynomial at that x value. So this right here would end up being, we subtracted those, take the function minus the polynomial at that value, then drop the negative because of the absolute value. As I said, ends up being 0.002036. So extremely close. Extremely close. And that's for only 1.4 away from the center. Notice since the Maclaurin polynomial, it's centered at centered at c equals 0. So this is still 1.4 away. It's only 0.02 off. But if we go a little further away, this now has polynomial at 2.1. Now I'm going to let's see what happens going further away. 2.1. Okay, now that's 0.896842. 0.896842. And then sine of 2.1. 0.863209. And if we figure out the error on that, that minus the polynomial at the point is going to drop my negative. It's going to give me 0.033632. Okay, so the error was a lot bigger than the previous error. Oh, you can see that, dang it. The error was a lot bigger than the previous error this time, and that's because we're just going further away. So the error for the 5th degree at 2.1, how does it compare to the error of the 5th degree at 1.2? It's bigger. It's a bigger error because we are further from center. Bigger error because we're further away from the center. And now it will get more accurate if we go with the 7th degree polynomial. So it gets more accurate no matter degrees, how far you, based on the degree of the polynomial. It also gets more accurate based on how close you are to the center. Okay, it is now 2:03. Let me see, how much do we have left in this packet? We won't do all of it. Oh, there's really only 2 more notes page. So I'll do most of the 2 more notes pages on Wednesday then. Awesome. Not much left. Based on that, any questions before we end?
So then for homework through today and before the next lesson, we should just go through starting at like the regular starting homework page, just go through and see how many we can.
Well, on the first homework page in the packet that we're currently working through, these questions right here are just asking you to come up with the Maclaurin polynomial for that degree that they tell you. So that's doable based on what we've learned so far. We did e to the x, and this is just going to be slightly different derivatives because of e to the negative x. We did sine of x without a coefficient inside there. It'll just be slightly different with a coefficient inside there because the chain rule. Both of those should definitely be doable based on examples we did, and just follow the formula for ones like these. This one, that's going to practice chain rule a lot. That's going to practice product rule a lot. I took off 5 and 6 because they were ridiculous. And if you go on the next page, it's 7 through 10 are just asking for Taylor polynomial degree and centered at the c value that they tell you. And so again, all of the 8 problems that I have for you of 1 through 10 are definitely doable based on what we've talked about so far, and a good practice for just coming up with a Maclaurin or Taylor polynomial. Any other questions? Okay, so other than working on this homework packet, I'd suggest either do some of the humongous review sheet that's sent out on the Google Classroom, as well as the limits practice that's on there. And then we will meet Wednesday. We will not meet Friday because we wouldn't meet Friday even if we had school, because Friday's Good Friday, student and staff holiday. Then when we start doing review starting next week, unless you want to, I don't see the necessity of us meeting as much as we have recently. Monday, Wednesday, and Friday. So we may only meet twice a week for the starting next week, but I'll let you know my decision on that Wednesday, and you'll find out more information about the next month as well.
Okay, so like no meeting at all, nothing for Friday.
No, because we wouldn't even have school Friday if this wasn't happening. So yeah, no meeting Friday. Relax and enjoy yourself Friday. Any other questions? Okay. Well, have a great day. Bye.
Thank you, Hunter. Thank you.
Yeah.